Question 5. A student investigated how the power output of a filament lamp varied with the current in the lamp. The diagram below shows part of the circuit used. So this is the IV graphs required practical. So let's carry on. Let's look at the questions. So to calculate the power output, the student measured the current in the lamp and the potential difference across the lamp. Complete the diagram by adding an ammeter and a voltmeter. So the ammeter is going to give us our potential difference. It says here potential difference is across, so that means that it must be in parallel. And the my mistake here. Ammeters measure current, and the current is just in the lamp, so that's going to be the current is going to be in series, and the voltmeter is your potential difference, and that is going to be parallel. And we must use the correct circuit symbols. So an ammeter is an M and a voltmeter is one of those. So in order to do this, we've got to add these into the diagram. So we're going to go back to here. So we can put this at any point. We're going to put our ammeter in series. So ammeter is just a circle with a capital A in it, just like that. And our voltmeter must be across the lamp. So we're going to put it like this in parallel with this lamp. Okay, so make sure you don't do either near the gap, so it must be continuous, and that's going to be our voltmeter. So that's what it should look like. We should have an ammeter in series and our voltmeter in parallel across the lamp, so that you can look at the difference between the amount of energy on each side. Which energy store in the battery decreases when the lamp is switched on? So energy stored in a battery is chemical. The chemical will reduce. What happens to the energy transferred by the lamp? So we're going to have the chemical store and the battery reducing, and then that's going to turn on the light. Obviously, light isn't a store of energy, so as energy is stored, what it's going to do is it's going to heat up the surroundings. So the energy transferred by the lamp is going to be it's going to heat up the surrounding. And it will be stored as thermal. Surrounding air, and eventually it will dissipate. The graph below shows the results. So we can see we've got it's not directly proportional, it's just a non-linear relationship here between current and power. Apologies for the yawn. Right, describe how varying the current affects the power output. So we're going to talk about how when we increase the current, what happens to the power. So we can see that increasing current increases the power. Okay, you can see that as the current goes across, the power is going up. You can see that. You've got a relationship that's sort of doing that. But it's that would be worth 1 mark. And this was worth 2. So we've got to talk about the shape of this line. It's not as simple because, what I just said there would be also true for that, and that would be a directly proportional relationship. And we haven't got one of those. So what we've got, so we would say that this is a non-linear relationship. What that means is it's not a straight line. So non-linear relationship as the current gets higher, the rate, so the speed of power output increases. So what I mean is, if we look at the gradient of the line here, it's like that. Whereas later on, when we've got higher currents, so that was like for a current of 1. So when we've got higher currents, let's say a current of 2, our gradient of the line is much steeper. It's like that. So that's what I'm saying, is that as the current gets higher, the rate of the power output is increasing, and that's represented by the steepness of the line. Take those off for now. Write down the equation which links current, power, and resistance. So we're just going to our physics data sheet, and we're looking for something that's got current, power, and resistance in it. So let's remove the last equation we did. Let's have a look. Current, power, and resistance. Current, power, and resistance. There's power, potential difference in current, that won't work. There we go. Power, current, and resistance. So it's P equals I squared times R. And as I said in an earlier question, write it down if it's asking you to specifically write the formula, because if we use the long case in, like we lose a lowercase I, or we don't show it properly, like our eyes don't look like uppercase I's, then we might not get the mark. So power equals current squared times by resistance. So let's write it exactly as that. So power, obviously you won't have the sheet in front of you, so it'll be a bit easier. Don't write in the highlighter. Power equals current, and it was current squared multiplied by the resistance. And that is P equals I squared times R. Determine the resistance of the lamp. So we have calculate resistance here, so there's a calculation. When the current in the lamp is 0.22 amps. So we'll highlight that. So let's write down. So we're going to use FIFA. So formula first. Formula we've just written there. So it's P equals I squared times I. P equals I squared times by R. Okay. The I in FIFA is to input. We don't know the power at the moment. The current is 0.22 amps. That is the standard unit, so we don't need to convert. But we must remember to square that, and we're going to times that by the resistance, which is an unknown. So we can't currently do this calculation with what we've input. We are trying to find resistance, so there must be a way of finding that power. Let's have a look. So I think what we need to do here is we need to go back to that graph. So because we've got a current power graph, so we can use the current and we can find that on the graph. So I'm just going to write it here. So we've got a current of 0.22 amps is what we're looking for. So where is 0.22 amps on here? All right, common mistake would just be to do this. 0.2, 0.21, 0.22, but we haven't checked the scale, so maybe that isn't correct. So let's just check it. So we've got, same as before, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. I'll write it here. So 10 squares is equal to 0.05. Yeah, that's right. Yeah, 0.05. It would have been easier to use this bit here. So 0.05 amps. So what is 1 square worth? So we have to divide that by 10. So we'll do the same on that side. So 0.05 divided by 10. Got the calculator again. Oh, wrong one. 0.05 divided by 10. 0.005. So 1 square is 0 0.005 amps. So if we are looking for 0.22, so that would be 0.2 205, 0.21, 0.2.5. So it's going to be there. All right, so that's going to be our point there. So that would be 0.22. All right, let's draw our line up. So if we do that, remember get your ruler, and we draw it up, and we actually hit that point there, which is lucky. We're going to draw that across, making sure to keep it as straight as possible using the ruler. And we hit this point here. So again, we're going to check our scale. So it's easy to check here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 squares equal to 0.5 watts. So 1 square divided that by 10 equals 0.05 watts. I can do that one in my head. So that would be 1.05, 1.1. So that is 1.1 watt. So we can use that in here. So we're just going to input it again. So 1.1 is equal to 0.22 squared times by R. So now we've got our formula to the point where we've got two values known, only one unknown value, so we're just going to rearrange. So that is the F, so we're going to fine tune this. So we need to leave R as the subject. So what we do is we do the inverse of what's happening to R. So it's currently being times by 0.22 squared. So what we're going to do is, well, what I'll do before I even do that is I think we should get that 0.22 squared out of the way, because quite often when I mark exam papers, that's the thing that happens. People do everything right, but they forget to actually do the square there, and then they end up losing a mark. So let's just get that out of the way. So we'll just leave that as 1.1 is equal to, and we'll do that squaring now. So 0.22, and we'll square it just by using the square button. So that would be, rather than 0.22 squared, it's 0.0484. And I just like to check that both ways. So we'll do it, rather than using the squared function, we'll do 0.22 times by 0.22, and we get the same answer. So pretty confident of that. Times by R. So that's the first stage of my fine tuning. Now it's a little bit easier to rearrange. So R, as I say, we need to be the subject, so we're going to do the opposite function that's happening to R. So we're going to divide this side by 0.0484, and when we do that, it's times by and divided by 0.484, so that would cancel to 1, so we'd end up with 1 times by R, but 1 times by R is just R. And if we've done it to that side of the equal sign, we've got to do it to the other side, so we divide 1.1 by 0.0484. So we end up with 1.1 divided by, I don't like to use the divide by, I like to use the fraction function, so divide by 0.0484 is equal to R. Okay, so let's do that. Let's go to our calculator and figure that out. So 1.1 fraction 0.0484, and we get the answer, so that's the A of the FIFA, is 22.7272. I think that's right enough. The reason I put the answer in and don't just write that on there is because I might need to convert it to a number of significant figures. So let's see if it asks us to. It doesn't, but we can see that the current here is 2 decimal places. So we'll keep our answer the same. So we'll draw a line here, and that will round to 22.7. That 7 there will round up that 2, so 22.73. 22.73, and we've got the symbol ohms, so we do not need to change that. All right, that is the end of question 5.